Welcome back to our discussions on reflection and refraction of light. In this episode, we are going to discuss about reflection of light in spherical mirrors, image formation in concave mirrors, image formation in convex mirrors, sign convention for reflection by spherical mirrors, mirror formula and magnification. Now we are going to explore the formation of images in spherical mirrors. The laws of reflections are applicable to spherical mirrors as well. Mirrors whose reflecting surfaces are spherical are called spherical mirrors. The reflecting surface of a spherical mirror may be curved inwards or outwards. A spherical mirror whose reflecting surface is curved inwards, that is faces towards the center of the sphere, is called a concave mirror. A spherical mirror whose reflecting surface is curved outwards, that is faces outwards the center of the sphere, is called a convex mirror. The curved surface of a shining spoon could be considered as a curved mirror where we observe erect and inverted images on it. The surface of the spoon curved inwards behaves as a concave mirror, while the surface curved outwards behaves as a convex mirror. Spherical mirrors form a part of a sphere. Now let us learn a few terms regarding spherical mirrors. The center of the reflecting surface of a spherical mirror is a point called the pole, which lies on the surface of the mirror, represented by the letter P. The center of the sphere, called the center of curvature of the spherical mirror, is represented by the letter C. It is not a part of the mirror, it lies outside its reflecting surface. We observe the center of curvature of a concave mirror lies in front of it, while it lies behind the mirror in case of the convex mirror. The radius of the sphere of which the reflecting surface of a spherical mirror forms a part is called the radius of curvature of the mirror, represented by the letter R. The distance PC is equal to the radius of curvature. The imaginary straight line passing through the pole and the center of curvature of the spherical mirror is called the principal axis. The principal axis is normal to the mirror at its pole, that is perpendicular to the mirror at its pole. When the light rays from infinity parallel to the principal axis falls on the concave mirror, get reflected and converges at a point on the principal axis of the mirror called the principal focus of the concave mirror. Hence it is called the converging mirror. In a convex mirror, the light rays from infinity parallel to the principal axis falls on the convex mirror, get reflected and appear to diverge from a point on the principal axis of the mirror called the principal focus of the convex mirror. Hence it is called the diverging mirror. The distance between the pole and the principal focus of a spherical mirror is called the focal length, represented by the small letter f. The reflecting surface of a spherical mirror is by and large spherical, hence has a circular outline. The diameter of the reflecting surface of spherical mirror is called its aperture, represented by the distance mn. For spherical mirrors of small apertures, the radius of curvature is found to be equal to twice the focal length, mathematically represented as r is equal to 2f, which implies that the principal focus of a spherical mirror lies midway between the pole and the center of curvature. Now we are going to discuss about the image formation in concave mirrors. Rules for representation of images formed by spherical mirrors. In a concave mirror, when the light rays from infinity parallel to the principal axis falls on the mirror, get reflected and pass through the principal focus of the mirror. A ray passing through the principal focus after reflection gets reflected parallel to the principal axis. A ray passing through the center of curvature after reflection is reflected back along the same path. A ray incident obliquely to the principal axis towards the pole is reflected obliquely, obeying the laws of reflection. In all the cases, the laws of reflection are followed. At the point of incidence, the incident ray is reflected in such a way that the angle of reflection equals the angle of incidence. Consider an extended object of finite size placed in front of a spherical mirror. Each small portion of the extended object acts like a point source of light. An infinite number of light rays originate from each of these points. But for our convenience and clarity, we consider the intersection of at least two reflected light rays that gives the position of the image of the point object. Now we are going to discuss about the image formation by a concave mirror for different positions of the object. When the position of the object is at infinity in front of a concave mirror, a real inverted, highly diminished, point-sized image is formed at the principal focus. When the object is placed beyond the center of curvature of a concave mirror, a real inverted diminished image is formed between the principal focus and center of curvature. When an object is placed at the center of curvature in front of a concave mirror, a real inverted same size object is formed at the center of curvature. When an object is placed between the center of curvature and the principal focus of a concave mirror, a real inverted enlarged image is formed beyond the center of curvature. When an object is placed at the principal focus in front of a concave mirror, a real inverted highly enlarged image is formed at an infinite distance and not on the screen. When an object is placed between the pole and the principal focus, a virtual erect enlarged image is formed behind the mirror. Concave mirrors are used as reflectors in car headlights, searchlights, hand torches, and table lamps to get a powerful parallel beams of light. It is used by doctors to concentrate light on body parts like ears and eyes. It is used in the field of solar energy to focus sun rays on the objects to be heated. It is used as shaving mirrors and makeup mirrors to see a larger image of the face. It is used in spotlight devices to produce intense illumination in a well-defined area in stage, film, television, ballet, and opera productions. It is used by dentists to see larger images of the teeth of the patients. Now we are going to discuss about the rules for formation of images in a convex mirror. In a convex mirror, a ray of light parallel to the principal axis appear to diverge from the principal focus. A ray of light directed towards the principal focus after reflection get reflected parallel to the principal axis. A ray of light directed towards the center of curvature after reflection get reflected back in the same path. A ray of light incident obliquely to the principal axis towards the pole of the convex mirror get reflected obliquely, making equal angle with the principal axis. In all the cases, the laws of reflection are followed. At the point of incidence, the incident ray is reflected in such a way that the angle of reflection equals the angle of incidence. When an object is placed at infinity in front of a convex mirror, a virtual, erect, highly diminished, point-sized image is formed at the principal focus behind the mirror. When an object is placed between infinity and the pole of the convex mirror, a virtual, erect, diminished image is formed between the pole and the principal focus behind the mirror. At any position of the object in front of a convex mirror, a virtual, erect, diminished image is formed behind the mirror. This is the view of the full image of the magnificent monument of Taj Mahal through a mirror fitted in a wall of Agra Fort facing it. Could you guess which is the mirror? Obviously, it is a convex mirror because it's the convex mirror that gives the full image of a distant object, although it is diminished. while it is not possible to see the full image of the distant object through a plane mirror or a concave mirror. Convex mirrors are commonly used as rear view mirrors or wing mirrors in vehicles. These mirrors are fitted on the sides of the vehicles, enabling the driver to see the traffic behind to facilitate safe driving. Convex mirrors are preferred because they always give an erect though diminished image. They give a wider field of view as they are curved outwards. Thus, convex mirrors enables the driver to view much larger area than would be possible with a plane mirror. Convex mirrors are often used for security purposes and hence found in the hallway of various buildings including hospitals, schools, stores, apartment buildings, hotels, and shopping malls. They are used to make ceiling dome mirrors and telescopes. They are also used as street light reflectors as it can spread light over bigger areas. Now we are going to discuss about a set of sign conventions called the new Cartesian sign conventions while dealing with the reflection of light by spherical mirrors. As per new Cartesian sign convention for spherical mirrors, the object is always placed on the left of the mirror and the light from the object falls from the left to the right. All distances parallel to the principal axis are measured from the pole of the mirror. All distances measured to the right of the pole are taken as positive, while all distances measured to the left of the pole are taken as negative. The height measured upwards perpendicular to the principal axis is taken as positive, while the height measured downwards perpendicular to the principal axis is taken as negative. Now we are going to discuss about the mirror formula for spherical mirrors. The distance of the object from the pole of the mirror is called the object distance, represented by the letter U. The distance of the image from the pole of the mirror is called the image distance, represented by the letter V. The distance of the principal focus from the pole of the mirror is called its focal length, represented by the small letter F. Mirror formula is given by 1 upon V plus 1 upon U is equal to 1 upon F. Magnification produced by a mirror is the relative extent to which the image of an object is magnified with respect to the object size. That is, the extent to which the size of the image of an object is either smaller or bigger with respect to the size of the object. It is expressed as the ratio of the height of the image to the height of the object, represented by the small letter m. If the height of the object is h, the height of the image is h dash. Mathematically, magnification produced by the mirror m is equal to height of the image upon height of the object. Symbolically, m is equal to h dash upon h. Magnification is also related to the object distance and the image distance as the ratio of the image distance upon object distance, V upon U. Hence, magnification is equal to h dash upon h is equal to V upon U.